Okay, the lift sling is used to hoist a container having a mass of 500 kilograms. Determine the force in each of the cables A, B, and AC as a function of theta. If the maximum tension allowed in each cable is 5 kilonewtons, determine the shortest lengths of cables A, B, and AC that can be used for the lift. The center of gravity of the container is located at G. Okay, so in terms of statics, this is a problem of equilibrium of a particle, which means that any free body diagram that we draw can be represented as a particle. Okay, so we're trying to analyze the tension in these slings. To do that, we'll end up analyzing the free body diagram of this ring here. But first, we need to determine F. And we can do that with a free body diagram of this entire system, of this entire assembly as a system. So yes, we do have these flexible cables, but everything is connected and the cables are taut. So even if this was moving at constant velocity, it would be moving as a unit. So you can treat this entire assembly as a system, and all of these internal forces, as far as this free body diagram is concerned, you can neglect. So we've got the weight. This container, the center of mass is here, and it weighs 500 kilograms, which, so that's its mass, so it weighs 4905 newtons. Okay, so acting here, okay, and then we're saying that these cables have negligible mass or weight, and I guess this is also negligible too, but you would think it wouldn't be negligible, this beam here, this lift beam. But according to the problem, the way the problem is stated, the only mass that is relevant is the mass of this container. Okay, so in this free body diagram here, we've isolated this system. There's only one other force, and that's this unknown force F. And as I mentioned at the beginning of the video, we could write a free body diagram of this system as a particle. We know this is in equilibrium, and the line of action of all of the forces acting on this system meet at a point. They meet anywhere along this line. So if we wanted to, we could have drawn our free body diagram as a particle, and so that's F. We could do with that. We could have treated it as a particle. Okay, but we're going to leave it like this. So we've got a free body diagram, but we need to put, any free body diagram needs to have coordinates. So X, Y, and where the origin of this XY coordinate system is located doesn't matter in this situation. We're just summing the forces in the Y direction, in this upward direction. Summing the forces in the X direction, in this left to right direction. Okay, so let's do that. Let's sum the forces. We know that the sum of the forces in the Y must equal 0. So F is positive, minus 4905 is equal to 0. So F is equal to 4905 newtons. Okay? So now that we know F, we're trying to analyze the forces in these cables here. That's what the question is about. So let's do a free body diagram of this ring here. Okay? So we know F is acting up on this ring. This is 4905. And then these cables, we know they're in tension. They're in tension because this ring is pulling this cable in this direction. We know that this ring is pulling this cable in this direction. So Newton's third law, the cable equal and opposite, that means the cable is pulling the ring in this direction. And also we know with cables, with rope, etc., the tension force is in line with the rope. We know the direction, so we know these directions, right? We know that the directions of each is in this direction. And so theta, you know that theta, this is theta from opposite interior angles, right? And this is, so FAB, the tension in cable AB, and the tension in cable AC. And once again, we could have represented this free body diagram as just a point. All of these forces meet at a common point. And it doesn't necessarily have to be at the center of mass when you're talking about equilibrium. We're neglecting the weight of this ring. Okay, so, but again, any free body diagram, you want to put your coordinates, your coordinate system. You could put the origin at the point where these forces meet, but we could also put it out here like this for this particular scenario. Okay, so you can apply your equations of equilibrium for each free body diagram. So let's sum the forces for this free body diagram. Let's sum the forces about the x direction. We know that this is in equilibrium. It's constant velocity or it's not moving. So the sum of the forces in the x must equal 0. So minus FAB, because this is going in the to the left, cosine of theta, plus FAC cosine theta is equal to 0, right? Well, the cosines of thetas cancel, and so what we're left with is that FAB is equal to FAC, and I think that you intuitively see that that's the case. The tensions in the cables are going to be the same. This problem is symmetric, but we just shown that officially here. Okay. So now let's sum the forces in the y. This also must be equal to 0. So minus FAB sine of theta, and then minus FAC, but let's just go ahead and substitute in FAB for FAC. FAB sine of theta, okay, now plus 4905, right, is equal to 0. So we get, this is so minus 2 FAB sine theta plus 4905 is equal to 0. So 2 FAB sine theta is equal to 4905. So to answer this question, it's the first thing it's asking us is determine the force in each of the cables AB and AC as a function of theta. The tension in the cables, the forces in the cables are the same. So let's just replace FAB with T and then put T as a function of theta. So like divide through by sine of theta and also 2. So what do we get? We get the tension in the cables, T, is equal to, so what is 4905 divided by 2? $2452.5. Okay, and this is newtons. So this is the answer to the first part of this question. Determine the force in each of the cables AB and AC as a function of theta. So the tension in either one of the cables is the same. It's the same force as a function of this angle theta is equal to this, and it's in newtons. Okay. So now, if the maximum tension allowed in each cable is 15 kilonewtons or is 5 kilonewtons, determine the shortest lengths of cables AB and AC that can be used for the lift. Okay, so let's copy this. All right, so what is the shortest length of cables you can use? So as theta gets smaller, the cable that you're using is getting shorter, and so the tension is getting higher, the tension in the cables. So what's the smallest theta, to where if you go any smaller than that theta, the tension in the cables is going to go above 5 kilonewtons. And once we have that theta, we can then find the length of the cable. So let's substitute 5 kilonewtons into this equation and solve for theta. But we're going to convert 5 kilonewtons to newtons, because our formula is in newtons. That's why we wrote newtons here. So 5,000 okay, so okay. Okay, so using the inverse sine, (29.37 degrees). Okay, anything smaller than that, the tension in the cables go above 5 kilonewtons. So at this theta, what is the length of the cables? So what we have is you've got 1.5 theta, and then I'm just going to put L, because I could put LAB, but LAB and LAC are the same thing. It's symmetric. Okay, so we can write that cosine of theta is equal to adjacent over hypotenuse. And so this is solving for L. You get L is 1.5 over cosine theta. So now we can substitute in our theta. Okay, so L is equal to 1.5 divided by cosine of 29.37, 1.72 meters. And that's the shortest length cables that can be used.